Welcome to the lesson on section 12.8 power series. In this lesson, you'll learn what a power series is and how to find its radius and interval of convergence. A power series centered at x equals a is a series whose nth term is made up of some constant multiplied by the nth power of the quantity x minus a. In expanded form, n equals 0 gives the constant c sub 0. N equals 1 results in the term c sub 1 times x minus a to the first power. N equals 2 gives c sub 2 times x minus a to the second power, and so on. This series always converges when x is equal to a. Why is that? If we were to substitute a in place of all the x's, the term when n equals 0 would be the constant c sub 0, but all of the other terms would be zeros. Thus, the sum would just be c sub 0. However, this series does not necessarily converge for other values of x substituted into the terms. Finding those values for which the series does converge will be the topic of the rest of this lesson. For my first example, consider the series 1 plus x squared plus x to the third, and so on. This is a geometric series with first term 1, common ratio x, and the sum of an infinite geometric series is a divided by 1 minus r. So for this series, it's 1 over 1 minus x. However, this is only valid when the common ratio has an absolute value less than 1. So this sum only holds true when the absolute value of x is less than 1. This leads us to the first of several power series that you'll have to memorize by the end of this unit. 1 over 1 minus x is equal to the infinite series 1 plus x squared plus x to the third, and so on. Let's apply some series-related vocabulary to what we just found. The interval of convergence of a power series is the set of all x values for which the series converges. The diagram shows a number line with a at the center. The parentheses surround the interval of convergence. Just as the distance from the center to the edge of a circle is called the radius, here the distance from the center A to the edge of the interval of convergence is called the radius of convergence. The brackets at the endpoints of the interval may be open or closed. You'll see in the following examples how to determine which is correct. This example refers back to our geometric series with first term 1 and common ratio x from example 1. Since the series converges when the absolute value of the common ratio is less than 1, the interval of convergence would be from -1 to 1. And the radius of convergence is 1 because the distance from the center to the edge of the interval is 1. This interval would not include 1 or -1. That's because when x equals -1, the series will alternate 1 minus 1 plus 1 minus 1 and so on, and that sequence of partial sums does not converge. Then when x equals 1, the series is 1 plus 1 plus 1 plus 1 and so on, which also does not have a finite sum. In example 3, I'll find the radius and interval of convergence for this power series x minus 1 to the n divided by n. To find the interval of convergence, I'll apply the ratio test. So I need to calculate the limit of the absolute value of the ratio between the n plus first term and the nth term. The x minus 1's reduced to a single x minus 1, and I'll gather the n over n plus 1 together because they're similar. I can see that n over n plus 1 goes to 1 as n goes to infinity. So this limit is equal to the absolute value of x minus 1. The ratio test says that the series converges if this limit is less than 1. So solving the inequality, absolute value of x minus 1 is less than 1. I can see that x minus 1 must be between negative 1 and positive 1. And then solving for x must be between 0 and 2. This makes the endpoints of the interval of convergence 0 and 2. There's a distance of 1 from the center to the edges of this interval, so the radius of convergence is 1. Now we need to test the series for convergence when x is equal to each of the endpoints. Substituting 0 for x, I get the series negative 1 to the n over n. This is an alternating series, so I could use the alternating series test to show this converges. It's actually the alternating harmonic series for which we've already proven convergence in an earlier lesson. Now I have to test for convergence at the other endpoint. Substitute 2 for x, and the series becomes 1 to the n over n, which is the harmonic series. It's also known as a p-series with p equal to 1, which is known to diverge. I've now shown that the series converges when x equals 0, but not when x equals 2. That makes the interval of convergence the interval from 0 to 2, including 0, but not including 2. This concludes the lesson on section 12.8, power series.